Welcome, and thank you for attending this talk. My name is Frédéric Recoules. I'm a PhD student in France at CEALIST, Université Paris-Saclay, and Université Grenoble-Alpes. I'm very proud to present you today a result published at ASE 19 about how to verify C code embedding new style inline assembly with state-of-the-art verification tools like, for instance, Klee. Indeed, informal verification have made tremendous progress over the last decades. Software verification remains a scientific challenge. There are still several issues to address in order to open formal methods to everyone. For instance, usability, learnability, or scalability. The challenge we focus on today is about supporting a language feature that used to be ignored by the vast majority of C analyzers. So, today's challenge is how to deal with C code embedding inline assembly. And in fact, we want our solution to be generic enough to directly work with off-the-shelf C analyzers. But, first and foremost, why focusing on inline assembly? Inline assembly is a special feature provided by some compilers like GCC or Celam, which allow us to directly embed assembly instructions inside the CS sources. It is actually pretty common to use it in software development, either to have access to the hardware or to manually optimize the code. For instance, we found that more than 10% of the packages written in C of the Debian distributions contains some inline assembly chunks. Another study by Rigger and al. Reports that more than 1/4 of the top-rated GitHub projects make some use of inline assembly. Inline assembly is mostly used when performance matters, like in time-sensitive context, multimedia applications, or widely used libraries. Yet, the problem is, inline assembly severely hinders the C verification tools. Of course, assembly is not C, and thus, what the assembly chunk is doing is completely unknown. This way, Klee used to stop the exploration of paths containing inline assembly. Other approaches, like over-approximation, are not necessarily better, because at the end, the imprecision will likely lead to useless results. For verification purposes, it is often possible to replace the assembly code by an equivalent C code or some sort of annotations. But this approach has several drawbacks. It's time-consuming, error-prone, and still, you are not verifying the current implementation. One can develop a dedicated analyzer that is aware of inline assembly semantics, but it would be a lot of effort for a solution that is not generic at all. So, our proposition is to automatically lift the assembly code to an equivalent C code. This way, the task of verifying assembly code will be less time-consuming and far more safer. Moreover, this approach is mostly suitable for any kind of verification technique. So, we want our approach to be widely applicable. It should not be tied to a particular architecture or compiler. We want it to be verification friendly, so it should help getting useful results with off-the-shelf analyzers. And of course, we want it to be trustable, because we want to use it in formal method context. So, for the first requirement, we will leverage existing binary lifter in order to support several architectures. We will use novel dedicated low to high level simplifications to reduce the complexity of produced C code. And finally, as opposite to validating the word translator tools, each C translation will be validated with a tailor-made equivalent checking. At the end, we evaluated our prototype implementations over more than 2,000 assembly chunks found in the Debian packages. Looking back at what existed prior to Uwork, no solution fully fulfilled our requirements, either because they were tied to a particular architecture or because they target only one verification tool. Indeed, we were the first one to consider the verification friendliness. And is it really important? Well, let's jump into the details. You can see here the basic workflow of our prototype with Tina. Starting from a C file containing assembly chunks, we compile it into binary object in order to lift it to a low-level intermediate representation. We are now able to output the representation with the syntax of the C, and we are done. This approach is generic, but yet, for now we are not doing better than the others. In fact, we identified 3 threats in the raw low-level translation that can still hinder the analyzers. Low-level computation, like mixing logical and arithmetic operation, tricks to save space or time, like packing multiple values in one register, or unusual and unstructured control flow. It may not be an issue, but it's not so common to use gotos in C code. To deal with these threats, we provide dedicated simplification like typing, high-level predicate recovery, unpacking, expression propagation, and loop normalization. Let's see them in action on a small example. Here on the right side is a straightforward translation of the 2 assembly instructions of the left side. We can find that the condition of the if statement is arbitrarily complex for what it has to do. So we are using the technique proposed by Judy and Hall to identify and replace the condition by a more natural predicate like greater than. And this way we can get rid of all the ugly computation of the old condition. Then several passes will normalize the code by adding some structure and propagate some of the type information coming from the C context. The expression propagation not only helps removing temporary variables, but also enables writing rules to perform syntactic dedicated simplification. At the end, the code is smaller, simpler, and so more amenable to verification. Okay, so there is several transformation, but why would we trust the result is correct? Well, our prototype do not use validated components. Let's see what are the threats. The first one is during the emission of the binary code. The second one is during the binary to intermediate representation lifting. The last one is during the transformation and C code emission. Yet, the first 2 ones are part of our trust base because they rely on common and heavily tested software. So the question is, how to trust Tina transformation? Well, each translation is validated by compiling back the produced C code and try to prove that the equivalence of the true intermediate representation. But program equivalence is an NP problem. Hopefully, the problem is far more restricted because we manage to preserve the control flow graph of the program. So basically, the validation is all about checking pairwise equivalence of basic blocks. Let's now jump to the experimental evaluation. I will focus on the applicability of Tina on the x86 Debian assembly chunks and the results of our experiments on Klee symbolic execution. So, basically, we run Tina on every single chunk we found in the source of packages in the Debian JC. So, about 3,000 chunks. About 85% are currently supported by Tina, and all of these in-scope chunks were successfully lifted and validated with an average time lower than 1 second by chunk. Now, what's about the verifiability? In order to measure the impact of several levels of simplification, we selected 58 functions from 4 key packages ALSA, FFmpeg, GMP, and LibView, and run different analyzers on them. Here are the results for the Klee symbolic execution. Obviously, without any lifting, Klee is unable to fully explore any function containing inline assembly, while 25 of them are small enough to be fully covered with a 10-minute timeout. The other functions have too many paths to be explored, but we can see that Tina transformation significantly increases the number of paths explored in the same amount of time. In fact, while Klee have no problem to deal with low-level operation, simpler constraints lighten the solver burden. So, even for resilient technique like symbolic execution, verifiability can matter. Let's end this presentation with a small announcement. Tina has of course some limitations that we are willing to leverage. Thus, we are looking for case study facing difficulties with inline assembly. If this is your case, do not hesitate to contact us. In conclusion, we saw that inline assembly hinders C analysis techniques, but Tina is able to lift the assembly chunk to a C code amenable to verification. Tina fulfills our requirement as it is widely applicable, verification friendly, and crossword free. In addition, I put here information about our latest work on assembly interface compliance. You can follow the activities on Tina on BINSEC website, especially for the Klee workshop. We just released an artifact for Tina. Give it a try. Thank you for your attention and feel free to ask any question.